Good morning. In this lecture series, we see about what are the different types of steps in FEA. Already last class we discussing about different types of style steps in FEA and FEM. Okay, in this class we discussing about the step number 4. It is called as a define as a material behavior. So the last lecture series is already discussing about different types of discretization, different types of steps of discretization, number of noding and elements, and displacement functions. Okay, and in this class, we're discussing about the define the material behavior. So what is the meaning of material behavior means? So we have to assume the strength of the material. Then we have to find out the what are the characteristics of the material. So for example, when I'm assume as an aluminum material, okay, so I give aluminum material after giving a load, what are the deformation, what are the what is called as elongation, tension. Okay, these are the factors I have to identify for the given material. Okay, so first of all, I have to choosing the defined material behavior in the ANSYS solver. Okay, the strain displacement and the stress strain relations are necessary for deriving the relationship for the finite element equation. For example, you have to consider as a one-dimensional deformation. So if you consider the one-dimensional deformation, the strain displacement relations is given by E is equal to du by dx. Okay. So here generally U is called as a displacement. Okay. And dx is called as a change in length. Okay. So but du is called as a change in displacement with respect to the change in length. That is simply represented as a du by dx. Okay. And also we have the referred as a small e is called as a strain. Okay. So, and is from this relation, we have to find the stress strain relationship by using of Young's modulus formula. So, the Young's modulus is basically defined as E. Okay. The Young's modulus is equal to nothing but stress by strain. Okay. So, stress is defined means called as a force by area, and the strain is defined as a change in length by original length. So, these are the basic differences. So, and also we have to derive the stress relation formula. Simply is called as a E is equal to sigma by E. So the sigma is a trans means for stress, and the direction of the stress is like a either tensile or compressive. Okay, and E is a strain. So the next step is a foremost thing for deriving the stiffness matrix. Okay, is a case by case the applications. For example, if you are solving the one-dimensional problem, the basic of stiffness matrix is AE by L, 1 minus 1 and minus 1 plus 1. So this derivation we have to derive, okay, by using of the assuming the one-dimensional bar element, and we have to apply the boundary conditions. After making the matrix formation, we have to make the or we have to derive the stiffness matrix equation. So for example, whenever I'm considering the element, okay, so I already told you what is the element, what is a node, okay. So if you have an element, it's having a two nodes, okay, the basic of two nodes, we have to find out the stiffness matrix for the corresponding element, okay. So and also giving the total stiffness matrix for the given element. So for example, I have to consider the two element. After considering the two element, I have to add them. I got a total stiffness matrix equation. So what is the basic stiffness matrix equation is I already told you it's like a AE by L 1 minus 1 minus 1 plus 1. So and also once we find out the total stiffness matrix for the respective element, and we have to substitute in the general equation. So what is the general equation is called as a F is equal to K into U. So basically F is called as a force matrix, K is called as a stiffness matrix, and U is called as a displacement. So case by case we have to change. Okay. So the force matrix, how much force can be acted at the each node numbers. Okay. That is a representation is called as a F1, F2, F3, and also F1. So I have told you, if I consider the two element, so the simply there are three forces are acted, and also three displacement are acted, and also two stiffness matrix is there. Okay, for I considering the two one dimensional bar, I consider as a two elements. Okay, so after substituting these data in a force matrix, and also we already find out the total stiffness matrix of the respective element, and substitute that, and we find out this displacement for the respective node numbers. For example, if I am fixing the any one of the node, for example, I consider my node number one is I have to fix. Okay, so if I am fix the node number, there is no displacement. Why? Because I have to fix the particular node number. The rest of the numbers, for example, the 2 and 3 having a displacement, the based upon the load you have to acted. Okay, so either it's like a tensile load or compressive load. So based upon the load acted on the given element, the displacement can be occurred. So by using of the solving the general matrix equation after applying the boundary condition for the respective node number, we got have to find out the displacement of the respective element and nodes. We have to find out. Okay. So these are the simple equation for the component or general force matrix equation. Is like F is equal to K into U. I already told you, F is a force matrix, K is a stiffness matrix, U is a displacement matrix. And also we have to equation can be derived by the following cases. The one is generally we call it as a direct equilibrium method, and one another is called as a variational method and weight residual method. Okay, so direct equilibrium method is called as the method is much easier to supply or apply for the line or one dimensional elements. So for example, if you're taking the variation method, in this method is a more easy to adopt the determination of the element equation for the complicated element, like an element having a large number of degree of freedom and is an axis of stress element, and plate bending element on the two or three dimensional solid and stress element. So this kind of problem we have to derive from the variation method. And the weight residue method is one of the essential method, is a Galerkin method, is useful for developing the element equation for the thermal analysis problems. Okay, so if I'm choosing the thermal analysis problem, the Galerkin method is a more adaptable method and also is accurate method to get the derive the accurate answer. And they are using for the especially based upon the useful when the functional or fractional such as the potential energy is not ready to available. So based upon your element, you have to choose the different types of cases. Thank you.